Okay. Good afternoon, everyone. Welcome to Section 5, Human Gameplay. My name is Professor Hsin-Hung from National China University, Taiwan. And it's my great pleasure to serve as chair of this session. In this session, we have two papers to be presented. Each presenter will have 20 minutes in total, including 15 minutes for presentation and 5 minutes for question. Okay, let's begin our session. Okay, the first paper is titled "Making KataGo HumanSL More Human-like for a Mature Level Play." The presenter is Chu-Hsuan Shi. Okay, please join me in welcome the first presenter to start presentation.
Okay, so I will first set up the timer myself. Thank you for the introduction. I'm going to share about our work on making KataGo HumanSL more human-like for a mature level play, co-authored with Kyota, Kuboki, Shi-Jim, and Kokolo Ikeda. The research on creating human-like AI agents received more and more attentions. And reproducing human players' behavior is important for entertaining or teaching human players. For example, we can use these human-like AI agents as the practice opponents or use them as test players of content generation. And gameplay behaviors involve many aspects. Taking broken as example, it may be the move itself or thinking time, resignation timing, and many others. In this work, we target the reproduction of the moves. To elaborate, we target the game of Go and aim to reproduce the average style human play at various skill levels. In Go, an often used metric is the down Q ranks, with 20 Q a weak player, and when it gets stronger, it will become 1 Q and followed by 1 dan to 9 dan. And the imagination is like this. We have a model and take the position as input, as long with the skill level. Then the model will output policy, that is the probability distribution of moves. Our main contributions include 3 factors. First, we evaluate human likeness of policies from several aspects. Second, we proposed a method called PAPM to enhance human likeness. Third, we show that the softmax-based selection enables finer skill level control. And a worth mentioning related work is Maya, which is a collection of models trained via supervised learning using human amateur chess games. In this work, the authors collected many chess games played by human players and grouped them into different rating tiers. For each rating tier, they use supervised learning to train a model. And in their experiments, they showed that better predictions was achieved when the training and test skill level were close. Later, the same group proposed Maya 2. And this is a unified model which takes the skill level as input and predict the corresponding policy output and other information. And the baseline of our work, KataGo's HumanSL. So I think KataGo is probably the most famous for it as an AlphaZero-like strong AI Go agent. But in last year, it included a HumanSL neural network into the project. And this network was trained on a large number of human game records. This model takes the position, the rank, and even the date as input, and output the policy and other corresponding information. We wonder whether such HumanSL model, the predictions by HumanSL really look human-like. And in first place, so how should we evaluate the human likeness? And common practice in supervised learning is that we just collect many human games and then make our model do predictions to see whether they match. So we collected 90 by 90 Go games played on a FoxGo server. And there is a FoxGo dataset covered game records with various range from 18K to 90. We sampled 1,000 games per rank. And those games are where both players played with the same rank. And at the same time, we compare several neural network settings. For the KataGo HumanSL, we use the 10 ranks from 19K to 90. We also intentionally include the Kata1 with the AlphaZero style to compare. So next, we are going to see how well these game records match with the predictions. And we will use several metrics including move matching accuracy, likelihood, and distance to the previous move. First is the move matching accuracy, which is used in many previous work. It calculates the proportion of states where the highest probability move matches the actual move. However, by taking the highest probability move, which means we do the argmax, it loses some information. Assuming that we have two moves, and model A predicts 90 to 10 for these two moves, and model B predicts 51 to 59 for the same two moves. By taking the argmax, they're going to play the same move, the first one, but actually the probability differs a lot. And that's why in a previous work by our group, we proposed to also see the likelihood to evaluate Shoki policies. So the likelihood is basically the geometric mean of the predicted probability of the actual move. So if we see the likelihood, we will calculate the probability, and 90 and 51 should make difference. So here's the result. The x-axis shows the rank from weak to strong, and the y-axis is the accuracy or the likelihood. And we have rainbow-colored curves representing different KH settings from weak to strong, and also the Kata1 with a black curve. And both the accuracy and likelihood are the higher the better. So we can see the Kata1 is the least human-like in both of these two metrics. Then when we take a closer look into these rainbow-colored curves, for weaker players on the left side, the red curves or orange curve, which corresponds to the weaker KH settings, those settings perform better for weaker players. And on the right end, for stronger players, the blue or purple curves perform the best. So these results are similar to previous studies. Then when we try to compare the move matching accuracy and the likelihood, we find the curve shapes are quite different, which means that they capture different characteristics of human likeness. So when evaluating human likeness, it is worth to see both. Additionally, we introduced another matrix, which is the distance to previous move. Our motivation is that so humans tend to play near the opponent's last move, and this tendency is stronger among weaker players. And I will skip the details of the distance calculation. So here is the first results. We do some statistics on the human moves in our collected game records, and those results are shown as brown dots. On the contrary, the Kata1's move distance to the previous move is quite high, and here is a big gap. And also from the brown curve dots, we see that weaker players tend to play closer to the previous move. So our hypothesis was verified. Then next, we are interested in the HumanSL result. Again, they are represented as the rainbow-colored curves, and even they become a bit closer compared to Kata 1. There's still a big gap. The statistics is still far from human statistics. And from these aspects, we say the Kata 1 is not so human-like. And here comes our proposed method, policy adjustment based on previous move, PAPM. We want to let the policy favor moves near the previous move. For example, assume white just played here, and black has some candidate move. Move A is close to the previous move, so the probability will be increased. Another move B, since it's far from the previous move, the probability will be decreased. The adjustment was achieved by reweighting those probabilities. And using a function looks like this. It has a parameter of slope m to control how the distance will influence the adjustment. So let's see how PAPM performs. And first we see the distance of the previous move. For game records from human players from weak to strong, here are the humans' average distance to the previous move. That is the brown dots we show in previous slides. And for the original HumanSL, the distance was a bit far, which also as shown earlier. With the PAPM, we test different slope parameter m. And we found that as the m increased, the distance to the previous move also decreased. This is as expected. And if we selected proper value of m, we can let the statistic close to the human statistics. So in this aspect, the human likeness has been improved. And how about other metrics? So we also see the accuracy and likelihood and find that they are also improved. And such improvement is larger among weaker players. This is, of course, a good news, but we wonder why this happens. And here shows a typical example why PAPM was so well. And this is a game from 1K players, predicted using KH1K. So the black just played here, and in the actual game, human play at this white circle. But the KH1K only gave it a 0.08 probability. In contrast, for this white triangle, it received a 0.72 because this is a strong penetration locally. And for Q-level players, so continuing the battle on the right seems natural, and PAPM avoided such kind of underestimation of the circle move. And this leads to the improvement of the accuracy and also likelihood. But so far, we have not yet discussed how to use those policies to play games. And actually, there's no established consensus. Some suggest to select the move with the highest probability, that is greedy, and some suggest just sampling from the distribution. And a previous work reported that the weights influence the scale levels. And we did, in our experiment, we let the KH networks to play against AI agents with known skill levels. And as previous studies shown, with the greedy, it tends to be too strong, and with sampling, it is a bit weak. And if we consider greedy as the probability in proportion to p to infinity and the sampling the p to 1, and it is natural to consider an intermediate version, which is p to rho and we can adjust the rule to adjust the playing strength. And such kind of softmax selection is often used in, for example, reinforcement learning. So with proper rule values, we see that we can successfully achieve a win rate close to 50%. And with these methods, we did a preliminary qualitative evaluation. A total of 6 evaluators attended these experiments. And we target the 2D setting with our proposed method version. And we select the states where the two policies differs a lot. And each evaluator helped us to check 20 policy pairs in a random order and blind manner. So they will see such pairs and select which one looks more natural. And here is an overview of the results. Among the 120 votes, our methods received 72. So we conclude that our method was generally perceived as more than human-like. And in most comments, they said that handling the local battle looks more natural. But there are also cases where the original HumanSL was favored. So this page will conclude my presentation, but I will not go into the details. So thank you for your attention, and I'm ready to answer any questions from the audience.
Okay, is anyone have any question for the presenter?
Yes, I would have a question. So I was wondering to what extent this PIPM approach would translate to other games, because it sounds like it could make sense to assume that human players tend to react to opponent moves by making moves close to the previous one, right? So, I mean, maybe even in chess or Othello. What do you think?
Othello may not be so suitable for chess-like games. I feel there is still some tendency that the weaker players tend to look at the move just played by the opponent. So maybe they will forget the rook or bishop in far away, just concentrating on the local area where the move just happened. Just my personal feeling, and I'm not so strong chess and chess-like players, and that I often do that.
Yeah, I assume especially for amateur players, that I guess that really might be just what they look at, right? They look at what just happened. How can I react to this this new situation over there?
Yeah.
Yeah. So very interesting. I like that.
Yeah. Thank you.
Okay, any other question? Okay, any other questions? We thank the presenter. This interesting and insightful presentations. Okay.
Thank you.
The presenter of the second paper is joined.
Hello. Everyone here. And you,
Oh, okay.
okay.
So Miss Lin will present the second paper.
Yes.
Oh, okay. The second paper is measuring strategy similarity between human and engine-generated Chinese chess opening trees. Authored by Lian Yang and Bo-Nian Chen, presented by Miss Lian. Okay, welcome next presenter.
Oh, okay. Let me share my desktop. Okay. Hello everyone. I want to presentation our work is in measuring strategy similarity between human and agent generates in Chinese chess opening trees. The opening phrase in Chinese chess is extremely vital. We observe the human players prefer stable and familiar classical variation, with their moves being heavily influenced by experience and the psychological factors. The standards is stark construct to modern AI agent. AI agent build strategies so deep search and self-play. They lean towards unconventional moves that deliver short-term advantage and explore new paths, even if it means momentary drop in win rates. This fundamentally different approach means their opening trees are structurally divergent from ours. This difference leads directly to our research objective. Pre-study have really focused on systematically measuring the degree of strategy similarity between human and AI. Our goal is not just to quantify this distance, but crucial to provide a clear direction for how future AI training and opening book optimization can more effectively incorporate the extent of human strategy. Moving on to our case study, we selected the cross-place kennel as our primary research subject. The rationale for this selection is clear. While it is less common in mainstream play, its variations are highly feasible. This easily leads to unconventional move board structure exploration, making it an ideal candidate for examining the strategy divergence between human and AI. Our objective is ultimately twofold. First, to compare the strategy evolution paths of both sides, and the second, to assess the feasibility of constructing a high-quality, high-coverage opening library source computer self-play. Our comparison is based on two datasets, the human opening tree representing classical strategies and our self-constructed agent opening tree. The core purpose of building this AI tree was precisely to evaluate the feasibility of using AI to generate a high-quality opening library. To ensure the AI tree persists sufficient breadth and diversity, we divided the construction into two paths. In path 1, we intentionally used a weaker AI agent like Xiangxi Wizard. We directly to conduct a high randomness search up to 10 play. The aim was to prevent the agent from over-concentrating on only the single structure variation from the start, allowing it to find potentially better unexplored paths. We then moved to the critically press 2, effectiveness validation. We use a much stronger AI agent to complete the subsequent position via self-play. This was crucial because it ensured every branch randomly explored in press 1 was validated in real match scenarios, yielding reliable win-draw-lose statistics. This also sets the foundation for our subsequent AI fleeting. Next is data quality control. Our objective is to fleet out the effective move from AI exploration and manage data quality, ensuring our comparison focus only on advantageous variations. To achieve this, we employed the advantage rations formula. These metrics adopt from existing literature allows us to perform consistent quality control across both opening trees, a standard and necessary step in data science. The interpretation is key. First, we assign high weight to wins. Second, and crucially, we include the log term. This term mitigates the artificially high score from small sample size, ensuring the only branches validated by sufficient gain counts and are deemed reliable and pace the AI filters. While we now have the AI scores in our subsequent analysis, we will set the specific AI threshold to control the required rigor for the retained strategies that enter the final comparison. First is sequence similarity. The measure the exact overlay of complete move sequence from the roots to the end of the path in both trees. However, it has crucial limitation. It only checks if a path overlay, but it not accounts for the frequency with which the path was chosen. This brings us to the second matrix, weighted coverage. This is our solution for handling frequency difference. We incorporate the visitation frequency of both sides, human and AI, for a single path into the weight calculation. This allows us to assess the practical utility of the AI strategy space in covering the human space. Together, these two metrics allow us to fully assess the practical coverage of AI strategies from the pace perspective. However, to understand the fundamentally difference in strategy structure, we must move to the node level comparison, which is the focus of the next slide. Pace similarity measured overlap, but it cannot solve the fundamental difference in tree structure. Our main concern is the topological disparity. The AI tree reaches 41 play, while the human tree only reaches 16 play. Direct comparison is skewed because the base number of deep AI branches distort simple similarity metrics. To overcome this, we adopt structural similarity SFN as our core metrics. Its goal is to quantify the divergence in strategies perform preference at every single node level. We designed a double normalization procedure to ensure a fair comparison. This involves two steps: frequency normalization, converting raw bits counts into strategy preference shares, eliminating the bias from different total gain counts. Structure normalization, performing common depth traction, strictly limiting the comparison range to depth equals 16 play. This focuses the analyze to focus on the core strategy space shared by both sides. After these rigorous procedures, we arrive at the SFN formula. This matrix provides the fairest and the most accurate quantification of the core structure divergence between human and AI. We now present the final value from our multi-level comparisons. First, the unweighted sequence similarity is only 2.8%, but through our weighted method, this value significantly improved to 8.9%. This validates that our weighting method is effective in capturing core strategy variations. The overall tree similarity measures 16.3%. This value is relatively higher than the sequence similarity suggestion that local decision nodes do overlap, but pace quickly diverge once a player commits to a full sequence. But here is the most critical data. After rigorous double normalization, the normalization structure similarity is only 12.5%. This value is relatively low, yet highly significant. This number clearly indicates that the structural divergence is profound, even in the core opening layer strategy files. Philosophy are fundamentally different. This sets the stage for the structural trends. Next, we examine the coverage results, which clearly demonstrates the asymmetry of strategy in the figure shown. Look at the right bar set. The weighted coverage is significantly higher than the unweighted. This validates the AI almost always has a valid counter to the core, most frequency human strategies. Now look at the right side. The AI human coverage is extremely low. The implication is that the human opening tree only covers a small portion of the AI's vast strategy space, particularly the innovative move explored by the agent. In summary, this asymmetry highly highlight the agent's comprehensive exploration versus the human's contrast stably. Our takeaway is that AI has mastered the core human moves, but structural, the AI strategy space is much wider. Now let's understand the coverage asymmetry. The next step is to examine how the AR threshold influence the coverage. This threshold acts as our parameter to control strategy rigor. We tested two thresholds like TAR equals 1.7 and TAR equals 1. TAR equals 1.7 cause the unweighted coverage orange to increase because we retain more low frequency branch. Crucially, look at the weighted coverage. It remains. This proves that the stricter threshold is better at preserving the most representative core strategy, avoiding interference from low-quality samples. Our conclusion is that the choice of AR threshold depends on the research objective. If you aim for comprehensiveness, use a lower threshold. If you prioritize representativeness and the strategy rigor, you should use a higher one. After all the fleeting waiting and normalization, we arrive at the final impactful conclusion of our study, the structure trends. Our final result is an SFN of only 12.5%. This is a significantly low value, powerfully confirming a fundamental structural divergence is strategy deployment between human and AI. To ensure the reliability of this finding, our data rigor was absolute. We employ string win rates around AR threshold, and the required minimum gain counts in n bigger than 10. This means we are comparing only high quality battle testing strategies. With that, divergence stem from two competing philosophies. Human strategy is characterized by concentrated stability. Players favor linear experience and the traditional choice, dedicating resources to a few proven branches. Conversely, AI strategy is driven by broad exploration. It retains a vast number of advantage validated branches at every single node. Thus, the AI opening tree maintains a clear structural trend from the human's focused thinking. To summarize all of our findings, we have two key conclusions. Comparing human vs AI strategy strengths, we successfully quantified the strategy strengths and the weakness of both sides, confirming a fundamentally divergence in their opening philosophy. Evaluating AI's feasibility for high-quality opening books. The comparison aids in assessing the feasibility of AI-generated opening books, provide a clear direction for optimization. Layers quantified strengths and weakness provides a clear direction for AI training and opening book optimization. It not only helps human players adapt to AI strategies, but also gives agent develop crucial insight for optimizing their opening book. Future work. Looking ahead to future work, we will focus on refining our measurement tool. We plan to introduce adapted threshold and extend an analyze to multiple agents with the automatic goals of constructing and validating a hybrid opening book. Hey, thanks for your listening. I can any question if you have any question.
Okay, Michael and Shay. I say Michael first. Okay.
I wanted to thank you for the talk. This was just applause in there, using the Zoom reactions. So thank you.
I have a question, and that is the question on, I would say the D max was 16, yes? And that is what I understand. That is your result to restrict it to 16. What happens if it is 18 or 14? It was in result 1, your first remark. Dus die structural normalization. And then you speak about the depth truncation, and you decided to restrict that to the D max is 16. Yes?
Yes.
My question now is, what happens if you say that the D max is 18 or the D max is 14? I do not ask for precise results, but I ask for a tendency, because then people get a little bit more grip on, I would say, the nature of the game.
Sorry, I didn't get. You mean 40 or 60 is about the number of game records or the game tree price, or
Yes, I mean the depth truncation. So you decide with all of you that we see it. Yes, there we have with the normalized structural similarity. Yes, and then you set that way you look and then you see significant difference between human and AI strategic choices. Yes, and I fully agree with that. And then you came up with, I would say, a result where you said the Dmax, the maximum depth is 16. Yes. And now my question is here simple. If you now set the maximal depth is 14 or the maximal depth is 18, I would like to have a feeling on which tendency it expresses. Let me come up with I would say, an adjacent question here. There's a significant difference between the human and AI strategic choices. Could you, I would say, specify it in one example? What is the human choosing and what is the AI strategic choice? Is the human choosing always for positional and the AI for complex and strategic or whatever? So it is up to you, but because I have no insight into this game, but that is the basis of my question.
The human expert is more likely to choose positions that they are familiar. So the game tree that human expert played or chose may be more concentrated, and the game tree that the AI generated or extended may be more diversity. So this difference can show that there are 16% is common for human and AI, and there are maybe 86% that human and AI choose different strategies. So AI is tended to choose more unreliable paths. So this may be this may not be correct in the future, but AI is trying to discover new strategies. But there may be some of them will be proven to be possible to be good paths. So the diversity is means that the opening book of the AI may not be may not be good as human experts, but maybe some passes, some moves in them may be useful in if we checked more if we played more game, there may be some interesting moves in the undiscovered moves.
Okay, if I understand, you aim at AI as learning from the human input.
What? Please, okay.
Yes. Okay. I think your work is very interesting, and what you say that there's significant difference between human and AI. That is absolutely true. Just my last question now is, do you think they coincide and that this problem, this difference between human and AI, will be, I would say, aligned, will be solved, are you aiming at the same output?
Uh, I, I, our goal is not to build an AI that can completely create the same as human expert. So I don't expect this value will be very high. For example, now this value is 16, and but maybe when the value is maybe 80 or maybe 100%, that means that is not our goal to make AI to completely follow the human strategy, but
Okay, thank you for your answer. I will say they are very insightful. I wish you good success with your, I would say, the further research you are aiming to perform.
Oh, thank you.
Okay, is there any question?
他的口音我这样没办法。
With no further questions, let's thank the presenter for their excellent work, and thanks everyone participate in this section. Okay, thank you.
Thank you. Thank you.
Thank you all.